In the previous part, we actually talked about the observable controller and the controllable controller. For observable controller, you're actually designing things, alright, based on a certain real system. So this is the real system. This is the system that you're designing, alright. So over at this side, alright, you're actually taking in values from the real system minus away values feedback from your design system. So you'll keep on alter and edit such that your design one can be modeled like your plants can be modeled the same as the real system. Alright, so you're somewhat actually modeling something that is unmeasurable. So at first things are unmeasurable. Alright, so after that, because of your designing over here, you're actually making things a little bit measurable. So you're actually making things measurable for yourself. So you can measure the state of the plant, and you can also model your state. Alright, so the observable purpose is actually this one. Alright, while the controllable one is simply straightforward. Alright, you are just simply controlling your plant. Alright, such that if you want certain reference signal, so you put in your reference signal, the feedback system over here will somewhat change things such that it will move towards the same as your reference signal. Alright, so if you want a reference signal to have 2 and output 2, alright, then you feedback this reference signal. Over here, the plant will own self change its systems such that it will feedback and feedback until it reaches this value 2. Okay, at first, if you input reference signal 2, it may not actually output 2, it may actually maybe output 0.5. So you need to keep on give different iterations such that upon a few iterations you can actually reach the output 2. Alright, then there will be no error over here. Alright, this is the summation between your reference signal and the feedback. The feedback tells you that whether is your system the same as the reference signal. Okay, so this is the controllable and this is the observable in a short and brief manner explanation. So there comes an explanation that I may not fully understand over at this page. Alright, it says that we can actually proceed by estimating unmeasurable states. Alright, in the presence of unmeasurable states, alright, we can proceed by estimating these unmeasurable states using an observer and then complete the feedback control. Alright, so we can actually feedback to our controller and then we can control our system in a certain sense. So by far I would think that you're actually saying that combining state feedback with an observer. Alright, so you want to have a feedback. Alright, so controllable system has its own feedback system, while the observable is just observable. So what I would suggest, I may be wrong, is that you have this minus kx hat over here, right? So you actually feedback all the way to here, I think. Let me see, give me a while. Okay, maybe not. Alright, I'm gonna rearrange this picture such that it looks like the controller. Okay, so how do I rearrange? Okay, I'm gonna somewhat take out this k, alright, since this is a x hat, right? So we want to also model something like a x over here. Alright, so give me a while. Okay. So I actually have this this plant, the signal from the plant, alright, feedback over at this side. Okay, while over here I would have a summation point, and this is the minus k. Okay, while our input, it's a certain reference signal. Alright, I call it r hat t. Alright, with its nu and nx. Okay, so I have this thing coming in and I have this thing coming here, and I'll have a double line over here because this will feedback vectors. Alright, this one also will feedback to vectors also. So minus k will feedback values. Okay, so this thing over here can be somewhat the same as this if you take a look. Alright, my estimator over here is simply like your x already. Instead of x, I write as x hat. Okay, or minus k, I bring it all over here. The summation point is the same. Remember to put plus and minus. Over here you put it as plus. Okay, So over here this is summation also, so it's a plus. So you may want to know how to draw this lah. Okay, but nonetheless this thing over here is somewhat the same as this one. Okay, so you have somewhat alter your observable system, somewhat like a controllable system. So within over here is a mixture of controllable and observable all together at once. Alright, so it's a very super powerful power pack Gaylord. I don't know how to say. And therefore at your this point, this is ut, alright, is equals to r hat t coming from your reference signal. Alright, maybe I should shift this this word up a bit. Alright, minus away the minus k times your x hat. Alright, so minus k times x hat, okay, which is the same as this one. Alright, this one actually comes from the next page. Alright, so I should paste it over here. So over here, as you can see, the next page actually say this thing. Alright, the one that you want to look at lah. Okay, you see, it's this particular, I should draw lah, this one. Alright, while your k is a series of vectors, if you think about it, your k is a series of vectors. Alright, so therefore yeah lor, so this is something, so the method of combining all this stuff, although I may still be wrong, alright, although I've drawn this but I may be a little bit wrong over at this side, I don't know, but at least you get to see a glimpse of how they try to, what is the thing that I want to see. Alright, and this method of combining stuff is called the separation theorem. Alright, so therefore over here, once you have the feedback, you can somewhat control your system also, right? This is somewhat like an observable controllable system. Alright, so it's a mixture of controllable and observable altogether. Alright, so therefore you can also somewhat change your k, alright, such that you can actually output a certain thing that you really want it to output, and things like that. So you can somewhat change what you want using the k, but you need a certain measurable from the observable. So you over here is somewhat observing what you want to look at. Alright, so nonetheless I may have required this one. So this ut over here will actually feedback to your model system. Your model system will actually feedback over here, and then I think this will be better. So this one over here is a summation between your output and your model, and then the difference will be put in over here, and this one will feedback to your full system. I think, I don't know, I'll leave you to think about it. It's quite complicated over here already, but nonetheless I just want to raise the awareness that in order to find a closed loop pose for this method, you can actually have a determinant, this thing a minus bk, if you still remember, is for your closed loop or your feedback system. This si minus a minus lc is your observable one. So as you can see, the observable multiplied by your controllable system. Your controllable, is a minus bk, you see. Okay, so your closed loop feedback is a minus bk. Your observable side is a minus lc. Okay, but just to take note that the state estimation error, your x hat, your x curly bar, alright, which is equals to x hat minus I think x minus x hat lah, I forget already, but anyway, this is the error, but this error cannot be controlled from the external signal RT, and this error x curly hat is not this one. Alright, it's not this one, this is x hat. Alright, so x hat is the estimated value, so x minus x hat, so this thing coming in, alright, is gonna feedback, is feedbacking x. Alright, so when you feedback x, so x minus, so you feedback x minus away this x hat, alright, for some arbitrary reason, I don't know how to connect, but anyway, you'll get x curly bar. Alright, so this is the error between your real system and the one that you're modeling. Okay, but it is, so this thing cannot be controlled, as it says, cannot be controlled from the external RT. So your reference signal, for some reason, aren't able to control how the xt will behave, because the plant itself is an unmeasurable system. It's something that you want to control, but it's something that you cannot measure. So you use the observable system to estimate the plant such that you can measure a little bit, and then you use your reference signal to because you want to design your stuff, so you also want to have a reference signal to design. Alright, so you use the plant's information to help you design your reference signal. Alright, so it's getting more and more chim already, right? Or in other words, you want a certain output, correct? You want a certain output, you want a smiley face, for example. Okay, so your reference signal, you know that you want something like a smiley face, so your reference signal must be the same as your output for some reasons. Alright, because you want to reference a certain signal such that your output will be the same as your reference signal, correct? So in order to output a certain smiley face, or you require a certain tool, alright, you requires a certain method, alright, such that it actually can output a smiley face. Alright, so this certain tool is something that we cannot measure, is unmeasurable, and therefore we use the observable one to actually measure and see what we can do, and then we can once we measured how it is being used, we understand how the plant is used, or how the plant is behaving, then we can slowly control the plant. So at first the plant, we don't know anything about it, then we start to measure it. Next, after measuring and knowing it better, we can control it, and control it already, we use it to help us generate our output. Alright, and basically the reference signal do nothing, it's just for us to want to refer to something to design output. Alright, so therefore the key issues is that you want to have a observable system to give you a measurable data, so that you can use the measurable data to control the things with regards or with reference to your reference signal. So your reference signal cannot change anything, but your observable one can, and the controller and the feedback, your minus k and your minus l, whatever, if you still remember, are the things that you would use to actually help you to control your observable systems. Alright, if you want to determine your stability, then you'll use this one to find your poles. Alright, so your poles will tell you the responses. Once you get the eigenvalues, then you'll get to know how the responses will behave. Is it fast, is it slow, things like that. Alright, which we have also discussed in previous videos talking about the roots. Alright, normally we want it to be minus maybe 300 or minus 100, or anything that is minus, because minus is in the left half plane of the S domain. Correct? And the higher value you are, alright, which is over here, which is for example minus 300, you're actually decaying faster. If you are somewhere near the origin, you're actually decaying slower. You see? So these are the things that you also want to consider, alright, when you're designing your controller and things like that. So the poles itself help you to determine that. And next, you may wonder, then what is this roots? Alright, why is it minus 300 then got like this? Why is it minus maybe 10 is like this? Because this is your S. S is equals to minus 300. Then this S, you're going to sub in into your transfer function. Alright, if you still remember, your transfer function is equals to whatever thing that you want. Alright, nonetheless, the transfer function can be in terms of this type of matrices, but this is for your poles. Alright, if you want to formulate for your transfer function, if you still remember, this one is for your open loop system. Alright, for your transfer function, you can sub in is, and then you can get a G of S. Alright, but as for our case, because it's so complicated, I'm also lazy to derive. Alright, then you can own self settle about. I don't think they will go into that detail, but you'll just take note that this is somewhat similar to what I've shown you in just now, that one. Alright, which is this one. Okay, this is your transfer function. If you still remember, derived from all the way, if you were to convert to the Laplace domain and you rearrange stuff. Alright, this thing over here is your transfer function, I think. Yeah, I forget already lah, but at least you get to see the differences. Okay, and therefore this above theorem that I've told you, this separation theorem, the one that we combine the controller and the observable system all together at once. Alright, like I've shown you in the pictorial graphics over here, although it's already something, doesn't look like a graph anymore. Alright, doesn't look like a diagram anymore, but at least you get to see all these things coming in already. Alright, cleaning our build a little bit. Alright, so this thing over here is the separation theorem. Alright, although this is a pretty neat method to do stuff. Alright, but it should be noted that the location of the closed loop pole is only one among many factors that come into the control system design. Alright, having to know the poles is one thing. Alright, because you may also be wary or be mindful, alright, that you also need to consider the sensitivity of your disturbance, the errors of a model, and a lot of feedback solutions, and other stuff. Alright, so you need to consider all the things that you haven't been able to measure. Alright, so although, as I say, the observable system is able to measure the things that is unmeasurable, but there are definitely some things that are still considered unmeasurable still. So these are the things that you may want to also be careful of. So normally, if you want to design things, please make sure you have a certain disturbance and model errors. Alright, so these are the things that you want to take note whenever you design certain stuff. Okay, and this sets as the last video for the whole system of this whole playlist, I think. Alright, so see you soon.